Today we're going to talk about the product rule for derivatives. So whenever you are taking the derivative of one function being multiplied by another function, you have to use the product rule. You can't just take the derivative of the first function and the derivative of the second function and multiply them together. So since we don't have a rule for this, the only way we can attempt to take the derivative of one function, u of x, times another function, v of x, is to write it out as a limit as h approaches 0 of u of x plus h, v of x plus h, minus u of x, v of x, all over h. Right? Because that's the limit definition of the derivative. F of x plus h minus f of x all over h. So we just evaluated both functions at x plus h, evaluated them both at x, found the difference between them, and divided by h. So what we're going to do here to actually figure out what this is, we're going to use a little trick that's often used to do some of these proofs, is we are going to just add a term into the numerator, and then again subtract that term also from the numerator. And so in this case, the term that's going to work out, and we'll see why as we go through this, is u of x plus h, v of x. So we're going to add u of x plus h, v of x into the numerator, and also subtract u of x plus h, v of x from the numerator. So effectively, we've not changed that numerator at all. We've added and subtracted the same thing, which should cancel out. Then what we're going to do is we're going to take a look through here, and we're going to group together this first term and this last term. And as we do that, we're going to factor out the u of x plus h. So we're going to have a limit as h approaches 0 of u of x plus h times v of x plus h minus v of x. And we're also going to factor out the v of x from this second two sets of terms here. We're going to factor the v of x out of that. So we're going to say plus v of x times a positive u of x plus h minus a u of x. And then this is all still going to be over h. And of course, one of the rules that we know for limits is that we can separate our limits out into multiple different limits. So I'm going to break this fraction down into two different limits separated by the plus sign in the middle. So that will turn this into a limit as h approaches 0 of u of x plus h times v of x plus h minus v of x all over h, plus a limit as h approaches 0 of v of x times u of x plus h minus u of x all over h. And as we do that, we can then take a look at this and break this down into four limits. Right? We can separate this into a limit as h approaches 0 of u of x plus h times a limit as h approaches 0 of v of x plus h minus v of x. And hopefully you're seeing why we're doing it this way, because the limit as h approaches 0 of v of x plus h minus v of x all over h should just be the derivative of v of x right here. And when we do this with the other side, we'll have a limit as h approaches 0 of v of x times a limit as h approaches 0 of u of x plus h minus u of x all over h, which is just the derivative of u of x. So as h goes to 0, u of x plus h just becomes u of x. And the limit as h approaches 0 of the difference quotient for v of x should be dv dx. And we'll add to that Well, the limit as h approaches 0 of v of x is just the v of x. And the limit as h approaches 0 of the difference quotient for u is just du dx. And this is what we call the product rule. Right? The derivative of u times v is u times the derivative of v plus v times the derivative of u. And this can be quite useful for us. We're just going to do a couple of basic examples right now because all we're able to do is use the power rule and the product rule. But once we get into some more complicated functions, trig functions and exponential functions and things like that, this is going to be exceptionally useful. So we'll take a look at this one. We're going to look for the derivative of x cubed plus 1 times x squared plus 3. Now, obviously, if we wanted to, we could distribute this together to get x to the 5th plus 3x cubed plus x squared plus 3. And it'd actually be a lot easier if we did that and then tried to take the derivative. So if we take the derivative of x to the 5th plus 3x cubed plus x squared plus 3, we'd end up with 5x to the 4th plus 9x squared plus 2x. Right? But that wasn't using the product rule. So let's show that if we use the product rule to take this derivative, we'll end up getting that same thing that we could get by distributing using the power rule. So dy dx should also equal, according to the product rule, the first function, x cubed plus 1, times the derivative of x squared plus 3. And the derivative of x squared plus 3 is 2x. And then it says we should take x squared plus 3, the second function, and multiply it by the derivative of the first function. Okay? And if we go through and distribute this out, we'll end up with 2x to the 4th plus 2x plus 3x to the 4th plus 9x squared. And when you combine that together, you get 5x to the 4th plus 9x squared plus 2x. Exactly the same as what we got if we just distributed to begin with and used the power rule. So either way you want to take these problems is just fine, but you do need to know the product rule because if I threw something out at you like e to the x times x squared, right? Once we knew the derivative of e to the x, we should be able to use the power rule to evaluate this derivative. Okay? But we can't distribute anything together to make it easier to do. So the power rule is, or the product rule is going to be very important. So we'll just practice it a couple more times. Here's our function u. Here's our function v. So our derivative, dy dx, should be u times the derivative of v, which is with the power rule, 2x plus 3, and then plus v times the derivative of u, using the power rule, that's just 3x squared. And if we want to, we could distribute all these things out and combine the like terms, which might be necessary to get an answer on a multiple choice question. But if you want to leave your answer like this, that's perfectly acceptable. There's nothing wrong with that on the AP test. They don't require you to simplify algebraic expressions. So we'll just leave it like that. And we'll do one more here. Here we've got u as x to the 1/3 and v as x squared minus 3x plus 2. And of course, we could distribute the x to the 1/3 through, but in this case, let's just use the product rule since that's what we're practicing here. dy dx is the first function times the derivative of the second function. So dv is 2x minus 3, and the plus 2 goes away because it's a constant. And then we'll add to that the derivative, well, we'll add that v, x squared minus 3x plus 2, times the derivative of u, is the power rule, that derivative to be 1/3 x to the negative 2/3. And again, this is an acceptable answer, but sometimes it might be necessary to simplify these down, factor things out of these, and kind of condense it down into one term. So we're not adding two things together. Let's think about how we might do that. Let's factor out x to the negative 2/3 from this and this. If I take an x to the negative 2/3 out of this first piece, the x to the 1/3 should actually just become x, right? Because x to the first times x to the negative 2/3 should be x to the 1/3. So we've got an x times a 2x minus 3, and we've got a plus x squared minus 3x plus 2 times 1/3. And that'll allow us to distribute the things inside the brackets, and it'll allow us to drop that x to the negative 2/3 into the denominator. So we'll end up with 2x squared minus 3x from the first piece here as I distribute that. And then the bottom piece will have, the second piece will have 1/3 x squared minus x plus 2/3 all over x to the 2/3. If we combine our like terms there, we'll end up with 2x squared plus 1/3 x squared, which would be 7/3 x squared, minus 3x and minus another x would be minus 4x, and the plus 2/3 all over x to the 2/3. And if we wanted to go even further, so we didn't have fractions there in the numerator, we could just multiply that 4x by 3 over 3 and drop the 3 to the denominator, giving us 7x squared minus 12x plus 2 all over 3x to the 2/3. And there's going to be reasons as we go through during our unit on applications of the derivative why it's going to be important for us to be able to take something like this up here, which is an acceptable answer, and turn it into a nice simplified version, because we might need to do some solving with this derivative. It's a lot easier to use this than it is to use that first one that we had up there. And that's the basics of the product rule. We'll come back and revisit this a lot as we learn how to take the derivatives of exponential functions and logarithmic functions and trig functions and inverse trig functions and all those things. But it's just another tool that you're going to need to have to make your way through unit on learning to take derivatives. And that's going to be it. Next time we'll talk about what happens when we have one function divided by another function. That's it for today on the product rule.